So, let us start lecture 44, and the course is on phase diagrams in single component and binary systems. And today's topic would be deviation from ideality and the formation of solution. In fact, till now whatever we have treated with the assumption that the solution formation follows ideal rule or law, and that is a Raoultian solution formation, where del H mix is considered to be 0. So, what does it mean? It means that whenever solution is formed considering the binary system A and B metals, so that solution while mixing would not lead to any enthalpy effect. The system would not absorb or give away heat from the system. So, but when we talk about non-ideality, then this del H mix, that is the mixing enthalpy, will not be 0. It can have either negative value or positive value, and it can have highly negative, highly positive and small positive, small negative. All the combinations can be possible, and accordingly the phase diagram would change, because the free energy composition diagram would also change, and consequently we will have when we consider the equilibrium between different phases, then we have to see the tangent, common tangent, and that common tangent would pass through different locations if we consider non-ideality than the location what we have seen in case of ideal solutions, and of course accordingly the phase diagrams will change. So, we will now consider that part, that non-ideality part, and in fact we have discussed non-ideality when we talked about Henry's law. And Henry's law, what we have seen, that if we consider a binary solution and if we consider very dilute solution, that time the partial pressure of any component in a solution phase, of course it is a homogeneous phase in a solution, would have a kind of proportionality with the composition in terms of mole fraction. Okay. So, that part we have seen, and how it deviates from Raoult's law we have also seen. We will also reflect today, but now this time we will not discuss that in terms of partial pressure, rather we will get into activity. Okay. We have defined activity in terms of fugacity, but we can also define activity in terms of the activity related to how activity relates to mole fraction of a component in a phase. Okay. So, let us start discussing non-ideality and formation of solution. So, now when we talk about formation of solution as well as activity considered as A, and let us say a component I at a particular temperature and pressure, okay, that is fixed, constant, that time that can be related to gamma I xi. Okay. In fact, when we talk about ideal, so that time ideal solution, that time AI equal to xi, but non-ideal cases, non-ideal solution AI not equal to xi, and this term actually decides the non-equality. So, in fact, when we try to talk about this, that means gamma I is equal to 1, but when we talk about this, that time gamma I could be greater than 1 or less than 1, and accordingly we will see how it satisfies Henry's law. Now, when we talk about activity in terms of gamma I, so we can actually talk about, let us say A and B, they are forming solution, and all the other assumptions like metal, and they are actually having same crystal structure, and they have nearest neighbor bonds, and also there would be 3 types of bonds. One is AA, BB as well as AB type, and accordingly that bond energy would decide whether a component taking away from the solution into the vapor phase would be decided by the relative negative values of those bond energies. Okay. That we have seen while discussing Henry's law. So, this time we will also take that particular thing into our discussion and see how the solution formation is actually getting influenced by this non-ideality. Now, here what we have seen, so this is binary, and let us take this to be metals and of same crystal structure. Okay. And here X A and X B are the mole fraction of A and B in the solution, and when you add them together it gives you 1 mole of solution. Okay. So, that is the consideration. Now, if I try to reflect activity and mole fraction, that is Xi. Okay. So, on a particular plot, let us see how it varies when we talk about ideality as well as non-ideality. Now, let us first talk about solution of B in A. Okay. So, that is the consideration. Okay. Now, when we talk about that, we can plot this is x b, here x b equal to 1, here x b equal to 0. Okay. Here x a equal to 0 and here x a equal to 1. Fine. Now, first case what we have considered solution of B in A. So, if I consider the activity when it is pure B, that time x b is equal to 1, and since there is no A, so there will be no point of considering any A B bond. So, it will be activity should be 1. So, this is point 1. This point reflects the activity equal to 1, and when we talk about 0, of course, that time activity of A would be 1, other one would not have any activity. So, it starts from 0 and it goes all the way to this. So, this is a straight line, and here activity of B equal to x b, where gamma b equal to 1, and remember this gamma b is nothing but activity coefficient. Gamma is activity coefficient. Okay, fine. So, this activity coefficient equal to 1. Now, let us say a situation happens where we have to now go for deviation from ideality. That deviation ideality could be positive or negative. It suggests that the composition, that activity of I should be, if I talk about positive, in this case activity of B should be more than activity of B when it is ideal. Okay. Similar on this is negative, A B should be less than A B ideal. Okay. These are the two situations we have to consider. Fine. Now, if it is greater than A B ideal, so that means the curve, so the curve would be going positive direction. Okay. So, this is A B greater than A B ideal. Okay. And that time, if let us say a situation arises like that, when we are talking about positive deviation from ideality, because this line is ideal or Raoultian behavior. Okay. So, this is now non-ideal with a positive deviation. Fine. Okay. So, if I consider x b tends to 0, what does it mean? That highly dilute solution of B in A. That is what we have considered. Okay. So, if you see this, we have considered that. Okay. So, when that case, we will see that AB is actually proportional to XB. Okay. And that case, it can be written as AB equal to gamma B XB, where this gamma B is a constant value. We will show it later why it becomes a constant. Okay. Now, in fact, this has a correlation with Henry's law. So, this becomes Henry's law. This is a correlation. If you recall, PB equal to a constant KB XB. So, this is also a statement of Henry's law. Okay. So, we get a situation like this. That case, we have to draw tangent from starting from 0 over this particular positive deviation plot. So, this is nothing but AB equal to gamma B XB, okay, and gamma B is a constant term. So, this is Henry's law. In fact, this one can also be written as PB, partial pressure of B in the solution of B in A, equal to KB XB. Okay. Now, when we talk about this, so now this can be, this two can be related to EAA, EBB and EAB. These are basically nothing but bond energies of AA bond, BB bond and AB bond. Okay. So, now since this one has a strong relation with this, you just recall our lecture on Henry's law. So, that means this should also be related to this, because the line is same, it can be same with respect to when we try to look at the partial pressure of B in equilibrium with the solution in a closed chamber at a constant temperature and pressure. Okay. So, this is bond energies. Now, why this happens, why positive deviation happens? We know that if we recall our discussion, we have taken a liquid solution and B in A, and we have tried to see whether taking out B from the surface of the liquid when the evaporation happens into the vapor phase. Now, when it is pure B, everything is BB type bond, or when it is pure A, everything is AA type bond. Now, if the AB bond energy, which is negative in sense, even BB as well as AA bond, all are negative quantity, because if you recall that bond energy appears when a particular metal is placed at an infinite distance and it is taken closer to another atom, the metal atom, to closer to, when we take it closer to another atom A. So, that means from infinite distance to closer to that A atom, there will be a situation that when we reach an equilibrium distance between two AA atoms, that happens due to the equilibrium between attractive and repulsive forces. So, that will be equilibrium, or we can say bond length or equilibrium distance, and that when that happens, that time the energy, the potential energy corresponding to the formation of that particular equilibrium distance between two metal is nothing but bond energy, which is negative in sense. If you recall, the curve looks like this. So, this is distance, we can say r, and this is positive, this is negative, and the potential energy curve looks like this. Okay. So, this is nothing but the bond energy. Fine, and this is potential energy. So, P is nothing but potential energy. Fine. Okay. So, now you see this is 0. So, the bond energy is a negative quantity. negative quantity. So, now here when the positive deviation happens, EAA and EBB are more negative than EAB bond energy. Okay. So, when this happens, so that means when it is pure, that means when we are considering solution of B in A, that initially everything was AA type bond and it has a highly negative value. So, that means A atom is sitting at a very a deep energy well. So, taking A atom would be difficult. Now, when we add B atom, since AB bond is now replacing AA bond, so that means an AA bond energy, AB bond energy is less than the AA bond energy. So, the positioning of B would be at a much lower, much shallower energy well. So, taking B would be easier. So, since taking B would be easier when we try to talk about evaporation from the solution of B in A at a particular temperature pressure from the surface of the liquid solution. So, that would be much higher. So, accordingly the partial pressure of B when we talk about this condition, that energy of EAA as well as EBB are more negative than EAB. So, taking out B would be easier. So, that is what it becomes positive deviation, fine. So, now similarly we can talk about a negative deviation. So, negative deviation happens when it goes downwards. Okay. So, this case AB is less than AB ideal. Okay. So, that time also we can have a tangent over this curve starting from 0, since the xp would be extremely low, hence it is a very dilute solution of B in A. So, we can draw another curve like this, another straight line. So, this would be A B equal to gamma B x B. So, this is also Henry's law, this is Henry's law again, fine. So, let us say this is 1 and let us say this is 2. So, we have talked about 1, okay. We have discussed about 1 and this is the condition for 1. Now, let us talk about condition 2 for 2. So, 2, that case we can also write A B equal to gamma B x B, and here gamma B is less than 1. Of course, the previous case gamma B was greater than 1. So, that is why it is a positive deviation, less than 1, and here we can also write P B equal to K B prime x B. So, this is what we have understood before. So, now this is the new way of expressing Henry's law. So, then this appears, if we recall, this appears if you recall, EAB energy, this EAB is more negative than EAA and EBB. Okay. So, if it is more negative, then taking away a B atom from the surface of the liquid solution when we talk about evaporation would be difficult. So, the partial pressure that would be in equilibrium with the solution in a closed chamber or closed system at a constant temperature and pressure. So, that partial pressure would be less than the partial pressure that would have been experienced had it been ideal. Okay. So, and because that time also we have difficulty in taking B out of the solution. So, now this K B prime is also constant. So, K B prime is also constant, and here this is also constant, and previous case also if you recall, if you see this K B here also constant and gamma B is also constant. Okay. So, now we see that the negative deviation happens when the solute atom taking away from the solute atom from the solution would be difficult. Okay. So, that is the condition when we talk about solution of B in A. Now, if we talk about, let us say we talk about solution of A in B, okay. So, similar situation can arise. So, that time if I draw, this is x A, it is going this way. So, this time x A equal to 0 and x B equal to 0 and x A equal to 1 and x B equal to 1. So, x A is varying from left to right, and then similar situation. So, this particular point would be A would be 1. Why? Because it is a pure A, and this straight line is having a relation A equal to x A, and this means gamma A equal to 1. So, that is this particular thing is condition of Raoultian solution. Fine. Now, here also we can have positive as well as negative deviation. So, positive deviation, let us talk about positive deviation. So, that time A should be greater than A when it is ideal solution. So, again if we talk about, if we consider x A, since I am talking about solution of A in B tends to 0. So, that means very dilute solution of A in B. Okay. So, that time we can also have a situation just like the previous case. We will have a plot like this, fine, and this is A greater than A ideal, and if we write in terms of A equal to gamma A, so this definitely greater than 1. Okay. Now, if we talk about very dilute solution, so that can be achieved if we draw a tangent to this non-ideal curve at x A equal to 0, we can have a straight line this. So, in fact, that time, so this can be written, with a condition that our activity coefficient A becomes constant. Okay. So, this becomes Henry's law. In fact, this is somewhat related to previous case what we have discussed, P A equal to K A x A, okay, and that time this can be achieved. So, this can be achieved, this is also Henry's law. So, this happens when EAA and EBB are more negative than EAB. So, that means definitely, as we have observed why taking B would be easy from a solution of B in A in case of, in the first case, the second case here also taking out A would be easy. So, that means the partial pressure in equilibrium with the solution would be more than the ideal cases. Okay. So, that time we can experience a positive deviation from ideality, that is Henry's law. Similarly, we can experience when negative deviation we consider. So, negative deviation we can have a plot like this. Okay. So, this is A, this is less than A ideal, and as we have seen that we have to draw tangent when x A tends to 0. So, this would be again A equal to gamma A x A, and here this would be gamma A is less than 1 and it is also a constant. Okay. In fact, if we talk about this part is also related to P A equal to K A prime x A. This is the statement of Henry's law, and these appears when E A B is more negative than E A A and E B B. Okay, fine. So, it will be very difficult to take out A from the solution of A in B, and that this Henry's law applies with a dilute solution. So, hence we see that Henry's law, which is deviation from ideality, appears when x A tends to 0 for A in B and x B tends to 0 for solution of B in A. Okay. So, that is the situation that appears. Fine. Just I missed a point. So, remember when we talk about gamma B is less than 1, this is basically talking about a negative, or I can put it here, this happens when a negative deviation from ideality happens. Remember here negative and positive does not mean that it is a value, it is positive or negative values, rather it is less than 1, it is greater than 1 or less than 1. So, that means it is deviation from ideal solution where gamma of that particular solute is 1 considering ideal, but here when we talk about Henry's it is away from that 1, it can be either positive either greater than 1 or less than 1. Okay, considering with respect to positive as well as negative deviation. Fine. So, that is the situation we are getting. Now, we can actually talk about, or we can say the relation of gamma I with delta H bar m I. So, if you recall, this delta H bar m I is nothing but the solution of or the component I is mixed in a solution, or the solution formation of I happens at a particular temperature pressure. That time the contribution of enthalpy that is coming up due to the mixing, that is nothing but this. This is molar partial molar enthalpy of I when mixing happens. Okay. So, then we can relate this like this. So, we can talk about delta G I bar m, and then we talk about this divided by del T. So, this is equal to minus delta bar m I by T square. Okay. So, this is Gibbs Helmholtz equation. So, now we can write, in fact, we can also see delta G m I equal to can be written as R T ln A I equal to R T ln gamma I plus R T ln x I. So, divided by T. So, T if we divide that, so this T would all get cancelled. So, now if we apply this, okay, and remember every time we are keeping pressure and composition constant. Fine. So, all cases pressure and composition constant. So, if that is composition is constant and xi is not a function of temperature and also R is a constant which is a gas constant. So, that time this term should be 0. So, then I can write should be equal to minus delta H bar m I by T square. So, from here it comes here. Now, we can use this conversion. We can write 1 by T equal to minus dt dou T square. Okay. See, if we write that, then this can become okay. So, this is equation. I am seeing a relation of gamma I with respect to delta H bar m I, okay, which is the mixing quantity, partial mixing quantity of ith component when it is mixed with the solution, okay, or solution formation of I. Okay. Now, this gamma I is actually is a temperature function of temperature. Now, we can have a situation. Okay. So, if this is the case, then we can have two situations. Situation 1 is like this: if gamma I is greater than 1. Okay. So, that time if we increase the temperature, the gamma I would decrease in order to a situation when gamma I would be equal to 1. It tries to achieve 1. Okay. If we increase the or we can say it tries to achieve ideality. Okay. Fine. Now, similarly, here what happens with the increase in temperature? The deviation from ideality is reducing. Now, here another situation we can have gamma I less than 1, that time if T increases, gamma I would increase in order to go into ideality 1. So, here we see that same ideality condition would be achieved. We see that there would be an adjustment in the gamma. Okay. Now, when we talked about positive deviation, we will see that delta H bar m I is actually positive, okay, greater than 0. Okay. What does it mean? It means that that it is an endothermic process. That means, when a component is added to a system, to a solution, or the component is made into a solution of A B, or let us say a binary situation. So, that time the system would try to absorb heat from the surrounding, okay, and the surrounding would get cooled down. Okay. So, this is endothermic process. Endothermic process, and in fact, solution formation is endothermic. Fine. And in this case, delta H bar m I is less than 0. So, that means the solution formation is actually exothermic. What does it mean? The solution system would release heat to the surrounding. Okay. So, that means there will be a lot of heat felt in the surrounding. So, now we could see as we go away from ideality, there would be always some sort of heat that enthalpy contribution when the solution is formed, or when a component is made into a solution with another component. Okay. It can be positive, it can be negative, okay. It can be greater than 0, it can be less than 0, and accordingly it can be endothermic process or exothermic process. Now, in case of ideal situation, so ideal situation, ideal case, when gamma I equal to 1, we see del H mix is equal to 0. Now, when we talk about these two, so when we talk about these two, in this case we will see delta H mix greater than 0, in this case delta H mix will be less than 0. Okay. When we talk about all the components would have a similar situation, let us say a kind of situation appears, you have a binary solution. If A is mixed into B or B is mixed into A, every time there would be let us say endothermic process. So, then enthalpy of mixing would also be endothermic, because enthalpy of mixing is nothing but. So, this can be written as delta H equal to X A delta H bar A m plus X B delta H bar m b if we talk about A B solution formation. So, then this would have that contribution, and that could be positive or negative. Now, since we see that gamma I from Henry's law, we see when gamma I is greater than 1. So, it means that E A B is less negative than E A A and E B B. It suggests that A A, because we know as per energy situation, the one which has a lower energy would like to be stable. Okay. We have seen all the time when we talk about equilibrium consideration, that system would always like to the lower energy level. Okay. Since these two having much lower, much higher negative value, so that means these two bonds are actually are more feasible than AB form formation. So, it means that AA bond and BB bond, so these two would be preferred. Okay. These two would be preferred, fine. Similarly, if we consider Henry's law gamma I less than 1, it appears that E A B is more negative than E A A and E B B. Okay. So, that time as per the discussion what we have, since A B bond has more negative value. So, system would like to achieve A B bond preferentially as compared to A A or B B. So, A B bond will be fine over A A or B B bond, fine. Fine. So, that means we can say that if delta H mix greater than 1, greater than 0, or so then we have this, and this means that the system would like to get phase separated. Phase separation. In fact, when we discuss phase diagram, you will see that the terminal solid solution formation is due to this delta H mix greater than 0. Okay. So, A B bond will not be preferred, rather A would like to have its own atom A and B would like to have own atom B. So, whenever you try to mix them, they would try to get segregated into AA as well as BB type. So, that is nothing but the terminal solid solution. Similarly, in this case del H mix is less than 0 as we have discussed. So, that time we have AB bond preference. So, it would be leading to a compound formation. In fact, intermetallic formation happens due to that. So, now you could see that del H mix value does change the way the different phases are appearing, and it would also lead to a change in the phase diagram. In fact, when we talk about G2 solution is nothing but G1 plus delta G mix, and here delta G mix is equal to delta H mix minus T del S mix. So, we have to apply this here G 2 equal to G 1 plus delta H mix minus T del S mix. So, now in the case of ideal solution, we have gotten G 2 equal to G 1 minus T del S mix, okay, since delta H mix equal to 0 for ideal case. But when we talk about this is ideal, now when we talk about non-ideal, this is non-ideal, let us say this one is non-ideal cases, delta H mix has to be considered whether it is a negative or positive value, and you could see so this one always tries to maintain randomness, okay, because minus T del S mix is always, if you recall the curve what it appears, it always goes down with the composition. If you try to plot this quantity minus of this quantity, it always goes down below 0. So, that means solution formation, that the random mixing of A and B, if I talk about binary solution, would be a possibility. But when you talk about this, if it is positive, then there will be a situation that some cases this value can actually supersede this minus T del S mix, and then we can actually get terminal solute solubility. And if it is negative, that can also lead to a situation of intermetallic formation. Okay. We can get those situations as we discuss onward. In fact, now our entire effort would be to quantify this value. Okay. How we can quantify? For that, we will be using a model called regular solution model. It can also be termed as quasi-chemical model. Okay. So, we will discuss this in our next few lectures, and then finally, we will go into free energy composition diagram again and try to see the equilibrium of different phases, and that time our entire consideration would be to see how G 2 of the solution varies. Okay. So, let me stop here, we will discuss more in our next lecture. Thank you.